So here's something worth thinking about as you settle in tonight. Every single place you've ever been, every room you've walked into, every road you've driven on, every bridge you've crossed without a second thought, somebody had to figure that out. Somebody had to look at a river and say, "We need to get across." Somebody had to look at a hill and say, "We need to cut through." Somebody had to look at soft, wet ground and say, "We're going to build something heavy right here, and it's going to stand for 100 years. That's civil engineering. It's the oldest form of engineering there is, and in a way, it's the most invisible. Because when it works, and it almost always works, you never notice it. You just live your life on top of it. And tonight, we're going to go through all of it, slowly. There's no rush. We're going to start at the very beginning, thousands of years ago, when people first started shaping the earth to suit their needs, and we'll work our way forward, through time, through stone and wood, and iron and steel and concrete and glass, through spectacular failures and quiet triumphs, through the lives of people who figured out things that nobody had ever figured out before. Some of this you might already know. Some of it, I promise, will surprise you. And if you drift off somewhere along the way, that's perfectly fine. That's kind of the point. The story will still be here. Let's start where it all starts, which is dirt. Literally, dirt. Because before you can build anything, you have to understand the ground beneath your feet, and for most of human history, people didn't. They just built things and hoped for the best. Sometimes it worked, sometimes it didn't. But the very first act of civil engineering, the very first time a human being deliberately altered the landscape to make life better, was probably something so simple you wouldn't even think of it as engineering. It was probably a path. Someone walking the same route, through tall grass often enough that the grass stopped growing back. Then maybe they moved a few rocks out of the way. Then maybe they laid some flat stones across a muddy stretch. And just like that, without any grand plan, they'd built infrastructure. But the real story begins with water. Water is the great motivator of civil engineering. If you look at the earliest civilizations, Mesopotamia, Egypt, the Indus Valley, ancient China, they all grew up around rivers. And rivers are wonderful and terrible. They give you drinking water. They irrigate your crops. They carry your goods downstream. But they also flood. They change course. They wash away everything you've built if you're not careful. So the very first large-scale civil engineering projects in human history were about controlling water. Think about Mesopotamia, the land between the Tigris and Euphrates rivers, in what's now Iraq. Around 5,000 or 6,000 years ago, the Sumerians were building irrigation canals, not little ditches, real canals, carefully graded so that water would flow from the river to the fields at a controlled rate. And here's what's clever about this. To make water flow where you want it, you have to understand slope. You have to know that water flows downhill, obviously, but you also have to figure out how much downhill. Too steep, and the water rushes through and erodes the canal walls. Too flat, and the water just sits there and goes stagnant. The Sumerians figured out how to grade these channels with a gentle, consistent slope over distances of miles. They did this without levels, without surveying equipment, without any of the tools we'd use today. They probably used water itself as their level, flooding a trench and marking where the surface sat, which is beautifully elegant when you think about it. Using the thing you're trying to control as the tool to control it. And these weren't just ditches in the ground. They built levees, raised banks of earth along the rivers to hold back floodwaters. They built reservoirs to store water for the dry season. They built gates and weirs to regulate flow. This is a whole water management system, and it's happening around 4000 BCE, maybe earlier. The entire Sumerian civilization depended on it. When the canals were maintained, the fields produced surplus grain, and the cities thrived. When the canals were neglected, during wars or political collapse, the fields dried up or flooded, and the cities shrank. Civil engineering wasn't just useful to these people, it was existential. Now, Egypt. You know about the pyramids, and we'll get to those, but the less famous and arguably more important engineering achievement of ancient Egypt was the management of the Nile. The Nile floods every year, or it did, before the Aswan Dam was built in the 20th century. Every summer, the river would swell with rainwater from the Ethiopian highlands, and it would overflow its banks and deposit a layer of rich, dark silt across the floodplain. That silt was incredibly fertile. It's what made Egyptian agriculture possible. But the flooding was unpredictable. Some years it was too much, some years not enough. So the Egyptians developed basin irrigation. They built low earthen walls to divide the floodplain into large, flat basins. And when the flood came, they'd open channels to let water into the basins, let it sit there for a month or so to soak into the soil and deposit its silt, and then drain it back to the river. This required an enormous amount of coordinated labor and planning. You had to build the walls, maintain the channels, decide when to open and close them. It was civil engineering as a social project, not just a technical one. And here's a detail I love. The Egyptians had a device called a nilometer, basically a well or a staircase or a column built into the riverbank, marked with measurements that let them track the height of the Nile as it rose and fell. Some of these nilometers were incredibly sophisticated. There's one on Elephantine Island near modern-day Aswan that dates back to at least the 3rd millennium BCE. It's essentially a gauging station. The priests would read the nilometer and predict how good the harvest would be, which determined tax rates for the year. Think about that. A piece of civil engineering infrastructure directly tied to economic policy 4,500 years ago. The water level in the river determined how much you owed the pharaoh. That's how fundamental this stuff was. But let's talk about the pyramids, because you can't talk about early civil engineering and not talk about the pyramids. The Great Pyramid of Giza was built around 2560 BCE during the reign of Pharaoh Khufu. It's about 481 feet tall, roughly the height of a 40-story building, and it's made of roughly 2.3 million blocks of stone, each one weighing an average of about 2.5 tons, some of them weighing 15 tons or more. And here's the thing that still amazes engineers today. The base of the pyramid is level to within less than an inch across a footprint of about 13 acres. 13 acres, and it's essentially flat. On bedrock, that isn't flat at all. They had to survey and level that ground with extraordinary precision before they laid a single stone. How did they do it? Honestly, we're still not entirely sure about every detail, and that's part of what makes it so fascinating. But we have good ideas. For the leveling, one widely discussed theory is that they cut shallow trenches into the bedrock, filled them with water, and used the water surface as a reference plane, similar to what the Sumerians probably did with their canals. Wherever the water surface was higher than the rock, they cut the rock down. Wherever it was lower, they filled it in. Water as a level. Simple, brilliant, and it works. For moving the stones, the most likely method involved sledges, wooden platforms dragged across sand. There's actually a famous painting in the tomb of Jehuti-Hotep, an Egyptian nobleman, that shows a large statue being transported on a sledge, and in front of the sledge, there's a figure pouring water onto the sand. For a long time, people thought that was a ritual, some kind of ceremonial act. But in 2014, physicists at the University of Amsterdam did experiments and found that wetting sand in front of a sledge reduces friction by about 50%. The water creates small bridges between the sand grains that make the surface firmer and smoother. So that painting wasn't showing a ritual at all. It was showing a real engineering technique. The Egyptians knew, through experience if not through physics, that wet sand was easier to drag heavy things across. And the ramps. There had to be ramps of some kind to get the stones up as the pyramid grew taller. The exact design is debated. Some researchers propose long, straight ramps extending out from the pyramid. Others suggest spiral ramps wrapping around the outside, and there's a fascinating theory by the French architect Jean-Pierre Houdin that proposes an internal ramp, a gently sloping tunnel built right into the structure of the pyramid itself, spiraling upward inside the walls. There's actually some evidence for this. Microgravity surveys of the Great Pyramid have detected what might be a spiral structure inside, but it's not confirmed. The point is, whatever method they used, it required extraordinary planning, logistics, and understanding of materials. You're coordinating tens of thousands of workers. You're quarrying stone from miles away. Some of the granite came from Aswan, over 500 miles to the south, and was transported by barge down the Nile. You're feeding and housing an entire temporary city of laborers. Recent archaeology has uncovered the workers' village near Giza, and it's clear these weren't slaves, as the old myth goes. They were skilled laborers and organized, crews, well-fed, with evidence of medical care. This was a national project, the Apollo program of the ancient world. Now, while Egypt was building pyramids, something equally remarkable was happening thousands of miles to the east. The Indus Valley civilization, in what's now Pakistan and northwest India, was building cities. And not just any cities. Cities with a level of urban planning that wouldn't be matched in Europe for thousands of years. Mohenjo-Daro and Harappa, the two largest cities we found, were laid out on careful grid patterns. Streets ran north-south and east-west, intersecting at right angles. The main streets were wide, up to 30 feet across, and the smaller lanes branched off systematically. But here's what really gets civil engineers excited: the drainage. These cities had covered drains running beneath the streets, connected to nearly every house. Wastewater from homes flowed into these covered channels and was carried out of the city. Some houses even had what appear to be indoor toilets connected to the drainage system. This is around 2500 BCE. For context, London didn't have a proper sewer system until the 1860s. The Indus Valley had one 4,000 years earlier. The bricks are worth mentioning too. The Indus Valley civilization used standardized bricks. And when I say standardized, I mean they had a consistent ratio of roughly 1 to 2 to 4 for height, width, and length. This ratio shows up across different cities hundreds of miles apart. That implies some kind of centralized standard, some agreement about how bricks should be made. Standardization is one of those quiet revolutions in engineering that doesn't get enough credit. When every brick is the same size, you can plan buildings more precisely, you can train workers more easily, and you can build faster. It's the same principle that would later drive the Industrial Revolution: interchangeable parts. The Indus Valley figured it out in the Bronze Age. So, by about 2000 BCE, We already have irrigation systems, flood control, monumental stone construction, urban planning, drainage networks, and standardized building materials. And all of this was figured out through trial and error, through observation, through generations of accumulated knowledge passed down from master builders to apprentices. There was no engineering theory yet, no mathematics of structures, no understanding of why an arch holds weight or why a wall collapses. That would come later, and it would come from a place you might not expect. Not Egypt, not Mesopotamia, but from the rocky, hilly, earthquake-prone peninsula of Greece. And Greece is where the story of civil engineering takes a genuinely surprising turn, because the Greeks didn't just build things, they started asking why things stood up in the first place. Now, Greece as a landscape is almost the opposite of Mesopotamia or the Nile Valley. There's no single great river to tame, no vast flat floodplain begging for irrigation canals. Instead, you've got mountains, rocky coastlines, islands scattered across the Aegean, and soil that's often thin and stubborn. Earthquakes are a regular occurrence. The terrain fragments naturally into small valleys and harbors, which is part of why Greece developed as a collection of independent city-states rather than one unified empire. And that geography shaped everything about how the Greeks approached building. They couldn't just pile up mud bricks the way the Mesopotamians did, because they didn't have endless clay. What they had was stone, limestone, marble, and lots of it. So Greek civil engineering became, above all else, the art of working with stone, and they got extraordinarily good at it. But here's what really sets the Greeks apart in our story. Before Greece, every civilization we've talked about, the Sumerians, the Egyptians, the people of the Indus Valley, they were brilliant practical engineers, but they were working from tradition and intuition. They knew what worked because they'd seen it work before. The Greeks were the first to start developing something like a theoretical framework. They wanted to understand the principles underneath the practice. Think about Thales of Miletus, working around 600 BCE. He's often called the first philosopher, but he was really more of a proto-engineer scientist. He traveled to Egypt, studied the pyramids, and reportedly calculated the height of the Great Pyramid by measuring its shadow and comparing it to the shadow of a stick of known height. Simple geometry, right? Similar triangles. But the revolutionary thing wasn't the math. It was the idea that you could use abstract reasoning to figure out something about the physical world without having to climb up and measure it directly. That's a fundamentally different way of thinking about building. And then there's Pythagoras, a generation or so later, and his famous theorem about right triangles. Now, the Egyptians and Babylonians had been using the 3-4-5 triangle for centuries to lay out right angles. The Egyptian rope stretchers, the harpodonapti, would take a rope with 12 evenly spaced knots, stretch it into a triangle with sides of 3, 4, and 5 units, and they'd have a perfect right angle every time. It worked beautifully. But Pythagoras proved why it worked. He showed that for any right triangle, the square of the longest side equals the sum of the squares of the other two sides. That's the leap from recipe to understanding, from knowing that something works to knowing why it works. And once you know why, you can generalize. You can apply the principle to situations nobody's encountered before. You're not limited to the specific cases your predecessors happened to try. This matters enormously for civil engineering, even though it would take centuries for the full implications to play out. The Greeks were planting the seeds of engineering science, the idea that you could calculate your way to a solution, not just build your way there through trial and error. Now, let's talk about what they actually built, because the structures themselves are remarkable. The most famous Greek contribution to civil engineering is probably the temple, and specifically, the system of proportions and structural elements we call the classical orders: Doric, Ionic, and Corinthian. You've seen these even if you don't know the names. Doric columns are the stout, sturdy ones with no base and simple capitals. Think of the Parthenon. Ionic columns are slimmer and more elegant, with those distinctive scroll-shaped vollets at the top. Corinthian columns are the most ornate, with capitals carved to look like acanthus leaves. But here's what's interesting from an engineering perspective. These aren't just decorative choices. Each order represents a different approach to the relationship between a column's height and its diameter, which is really a question about structural efficiency. A Doric column is typically about 4 to 6 times as tall as it is wide at the base. An Ionic column might be 8 or 9 times its base diameter. The proportions affect how much weight the column can carry, how it distributes load to the foundation, and how it behaves under lateral forces, like, say, an earthquake, which the Greeks had plenty of reason to worry about. The Parthenon, built between 447 and 432 BCE under the direction of Phidias, with architects Ectinus and Callicrates, is the masterpiece of this system. And it's full of subtle engineering tricks that most people never notice. The columns aren't perfectly straight. They have a slight swelling about a third of the way up called entasis. For a long time, people thought this was purely an optical correction, making the columns look straight to the human eye. And that's partly true. But there's also a structural argument. A column with a slight bulge is actually stronger under compression than a perfectly cylindrical one because it better resists the tendency to buckle. The Greeks may have figured this out empirically, or they may have been thinking about it more deliberately. We're not entirely sure. The Parthenon's base isn't perfectly flat either. It has a very slight upward curve, about 60 millimeters over a span of nearly 70 meters. Again, this is partly optical, preventing the base from appearing to sag in the middle. But it also helps with drainage, which is a very practical civil engineering concern. Water pooling on a flat stone surface is a recipe for erosion and frost damage. That gentle curve sends rainwater flowing outward to the edges. Beauty and function, working together. And the precision of the stonework is staggering. The column drums, the cylindrical sections stacked to form each column, were ground so precisely that they fit together without mortar. The joints are virtually invisible. The Greeks achieved this by a process of patient grinding, rotating one drum against another with fine abrasive sand between them until the surfaces mated perfectly. It's slow, painstaking work, but the result is a joint so tight that it's actually stronger than a mortared one, because the full surface area is in contact and sharing the load evenly. But temples, impressive as they are, aren't really the Greek contribution that matters most to the long arc of civil engineering. Let's talk about water, because the Greeks faced a real problem. Their cities were growing. Their natural springs and wells weren't always sufficient, and unlike the Egyptians or Mesopotamians, they couldn't just dig canals from a nearby river. They had to move water across rugged terrain, over valleys, around mountains, sometimes for miles. This is where we meet one of the most impressive and underappreciated pieces of ancient engineering: the Tunnel of Eupalinos on the island of Samos. Built around 530 BCE, this is an aqueduct tunnel running roughly 1,036 meters straight through a mountain, Mount Castro, to bring water from an inland spring to the city on the other side. And here's what's remarkable about it. They dug from both ends simultaneously. Two teams started on opposite sides of the mountain and worked toward each other, and they met in the middle with only a small deviation. Think about what that requires. You're underground, in the dark, with no GPS, no laser levels, no way to see the other team. You have to maintain your heading and your grade, the gentle downward slope that keeps the water flowing, using nothing but geometry, plumb lines, and very careful measurement. Herodotus, the historian, visited Samos and was so impressed that he listed the tunnel as one of the 3 greatest engineering works in the Greek world. And when modern surveyors examined it, they found that the 2 headings were off by only a few meters when they met, at a depth of more than 150 meters below the mountaintop. In the 6th century BCE. That's extraordinary. The method they likely used involves something called counter-tunneling. Essentially, running a series of connected shorter tunnels, or trenches, over the top of the mountain to establish a line of sight, then transferring that alignment underground through vertical shafts. It's clever, it's labor-intensive, and it works. The same basic principle would later be used in tunnel engineering for the next 2,500 years. So the Greeks gave us the beginnings of engineering theory, extraordinary stone construction, and sophisticated water infrastructure. But they had a limitation, and it's a big one. Greek architecture is fundamentally a post and lintel system, vertical columns supporting horizontal beams, and a horizontal stone beam can only span so far before its own weight causes it to crack. Stone is strong in compression. You can stack enormous weight on top of it, but it's weak in tension, meaning it doesn't handle being stretched or bent very well. When a stone beam spans a gap, the bottom face is in tension, and that's where it fails. This is why Greek temples have so many columns. The spans between them are relatively short, because longer spans would require thicker beams that would eventually become too heavy to support themselves. The Greeks knew about arches. They used them occasionally in gates and underground structures, but they never embraced the arch as a primary structural element. That would be the signature contribution of another civilization entirely, one that was, during the later Greek period, already rising to power on the Italian peninsula, the Romans. And the Romans didn't just build things. They built infrastructure on a scale that wouldn't be matched for over 1,000 years. If the Greeks gave civil engineering its brain, the Romans gave it its backbone. Here's what you need to understand about Roman engineering. It was driven by an empire. When you're governing territory that stretches from Britain to North Africa, from Spain to Syria, you need roads. You need bridges. You need aqueducts to supply your cities with water. You need harbors to move goods and troops. You need sewers to keep your cities livable. The sheer scale of the Roman administrative and military machine created engineering problems that demanded engineering solutions, and the Romans were nothing if not practical problem solvers. Let's start with roads, because Roman roads are foundational, literally. The Roman road network eventually covered something like 400,000 kilometers, with about 80,000 kilometers of that being major paved highways. The most famous, the Via Appia, the Appian Way, was begun in 312 BCE under the censor Appius Claudius Caecus, and it originally connected Rome to Capua, about 210 kilometers to the south. It was later extended all the way to Brindisi on the southeastern coast, a total distance of over 560 kilometers. What makes a Roman road remarkable isn't just its length, it's its cross-section. A well-built Roman road was essentially a layered engineering structure. At the bottom, you had the statumen, a foundation layer of large stones. Above that, the rudus, a layer of smaller stones often mixed with lime mortar. Then the nucleus, a finer layer of gravel and sand, sometimes with cement. And on top, the summa crusta, or pavimentum, the actual road surface, typically large flat paving stones carefully fitted together. The whole structure could be a meter or more in total depth. The road was crowned, higher in the center than at the edges, so that rainwater would drain off to ditches running along both sides. This is, essentially, the same basic design philosophy used in modern road construction. You have a strong foundation to distribute loads, progressively finer layers to create a smooth surface, a camber for drainage, and ditches to carry water away. The Romans figured this out 2,000 years before asphalt. Some of their roads are still visible today, still carrying the occasional footstep, the stones worn smooth by centuries of use, but the structure fundamentally intact. And the roads weren't just flat surfaces, they required bridges. Roman bridge engineering is where the arch really comes into its own. The semicircular stone arch became the Romans' signature structural element, and for good reason. An arch converts what would be a bending force in a flat beam into compression throughout the entire curved structure. Every stone in an arch, each one called a voussoir, is being squeezed by its neighbors, and stone loves compression. The forces flow down through the arch and into the abutments on either side, which push back and keep the whole thing stable. As long as the abutments don't move, the arch holds. It's elegant, it's efficient, and it allows spans far greater than any stone beam could achieve. The Pont de Gare in southern France, built around the middle of the 1st century CE, is probably the most famous Roman bridge aqueduct. It stands nearly 49 meters tall, 3 tiers of arches carrying a water channel across the valley of the Garden River. The bottom tier has 6 arches, the middle tier has 11, and the top tier, the one that actually carries the water, has 35 smaller arches. The whole structure was built from locally quarried limestone blocks, some weighing as much as 6 tons, fitted together without mortar. The stones are held in place purely by their own weight and the geometry of the arches. It's been standing for nearly 2,000 years. But here's what's really clever about the Pont du Gard and about Roman aqueducts in general. The water channel at the top has a gradient, a very slight downward slope, of roughly 1 in 3,000. That means for every 3,000 meters of horizontal distance, the channel drops about 1 meter. Over the entire 50-kilometer length of the aqueduct system that the Pont de Gare is part of, the total drop is only about 17 meters. That's an average grade so gentle that you could barely perceive it with the naked eye, and yet it's enough to keep the water flowing by gravity alone, no pumps needed, delivering something like 40,000 cubic meters of water per day to the city of Nemausus, modern Nimes. Surveying a gradient that precise across 50 kilometers of varied terrain, including river crossings and tunnels, using only tools like the groma and the chorobates, the Roman equivalents of a surveying cross and a long spirit level, is an achievement that still impresses modern engineers. The chorobates was essentially a long wooden bench, maybe 5 meters long, with a water channel cut into the top surface. You'd fill the channel with water, and when the water was level in the channel, you knew the bench was level. Simple, but effective. And with patience and care, accurate enough to lay out gradients measured in fractions of a degree over enormous distances. The Romans didn't build just one aqueduct. The city of Rome alone was eventually served by 11 major aqueducts, built over a span of about 5 centuries, collectively delivering roughly 1 million cubic meters of water per day. That's about a cubic meter per person per day for a city of 1 million people, a per capita water supply that many modern cities would envy. Frontinus, who served as Rome's water commissioner around 97 CE, wrote a detailed treatise on the system, De Aqua Eductu. That's one of our best sources for understanding how it all worked. He was clearly proud of the system, and couldn't resist comparing it favorably to what he considered the useless pyramids of Egypt and the famous but impractical works of Greece. Compare such numerous and indispensable structures carrying so much water, he wrote, with the idle pyramids or the useless, though famous works of the Greeks. A bit harsh, maybe, but you can hear the engineers' pride in infrastructure that actually serves people every single day. And then there's concrete. Roman concrete, opus cementitium, might be the single most consequential material innovation in the entire history of civil engineering, and it came about because of a volcano. Well, sort of. The Romans discovered that when you mix lime with a particular type of volcanic ash found near the town of Puteoli, modern Pozzuoli, near Naples, you get a material that sets hard even underwater. This volcanic ash, which we now call pozzolana, reacts chemically with lime and water to form calcium silicate hydrate compounds, essentially the same chemistry that makes modern Portland cement work. But the Roman version had a trick that our modern concrete doesn't. It actually gets stronger over time when exposed to seawater. Recent research has shown that seawater percolating through Roman marine concrete causes the growth of interlocking mineral crystals, specifically a mineral called tobermarite, that progressively reinforce the material. Modern concrete, by contrast, degrades in seawater. Roman harbor structures that have been submerged for 2,000 years are in some cases stronger now than when they were built. We're still trying to fully understand how to replicate that. With concrete, the Romans could build things that were simply impossible with cut stone alone. They could pour it into forms of any shape, build on irregular terrain, construct underwater foundations for bridges and harbors, and, most spectacularly, they could build enormous vaults and domes that enclosed vast interior spaces without any columns or supports in between. And this is where Roman engineering goes from impressive to genuinely breathtaking. Think about the problem of roofing a large space. If you're working with timber beams, you're limited by the length and strength of the wood. Maybe 10 or 12 meters before things start sagging dangerously. If you're working with stone lintels, like the Greeks, you're even more constrained because stone is so weak in tension. The Parthenon's interior columns are spaced barely 4 meters apart for exactly this reason. But with concrete, you can create a continuous shell, a curved surface that carries loads primarily in compression, flowing the weight smoothly down and outward to the walls. And since concrete can be poured into any shape, you're not limited to flat surfaces or simple curves. You can build a hemisphere. You can build a barrel vault, essentially a long, continuous arch. You can intersect 2 barrel vaults at right angles to create a groin vault, which concentrates the load at 4 corner points and opens up the walls in between. The Romans figured all of this out, and they did it without calculus, without structural analysis software, without even a formal theory of how forces move through curved surfaces. They did it by building, observing, and refining. By intuition sharpened over generations. The absolute masterpiece, the building that still makes structural engineers shake their heads in quiet disbelief, is the Pantheon in Rome. Built during the reign of Emperor Hadrian, completed around 125 CE, the Pantheon has a dome that spans 43.3 meters. 43 meters of unreinforced concrete, forming a perfect hemisphere that sits atop a cylindrical drum, with a 9-meter-wide open hole at the top called the oculus. No frame, no rebar, no steel, just concrete and brilliant geometry. And here's the thing. that 43.3-meter span was not surpassed for over 1,300 years. Not until Brunelleschi built the dome of Florence Cathedral in 1436. And even then, Brunelleschi's dome used a completely different structural approach. The Pantheon's dome is a monolithic concrete shell. Nothing like it had been built before, and arguably nothing quite like it has been built since. So how does it work? How does an unreinforced concrete dome that wide stay up? The answer is a combination of geometry, material grading, and the step rings you can see on the exterior. The dome is not a uniform thickness. It's about 6 meters thick at the base, where it meets the drum, and tapers to only about 1.5 meters at the oculus. That means most of the weight is concentrated low, near the supports, which is exactly where you want it. But even more clever is what's inside the concrete itself. The Romans varied the aggregate, the chunks of stone or brick mixed into the concrete, based on where they were in the structure. Near the base, the aggregate is dense travertine and tufa. As you move up the dome, it transitions to lighter brick fragments. And near the top, the aggregate is pumice, volcanic stone so light it floats on water. The Romans were effectively grading the density of their concrete to reduce the weight at the top of the dome, where it would create the most outward thrust. They were doing what a modern engineer would call material optimization, and they were doing it in the 2nd century. The coffers, those beautiful recessed square panels on the interior surface of the dome, aren't just decorative either. Each coffer removes material, reducing weight, without significantly reducing structural capacity, because the ribs between the coffers act as a network of arches channeling forces downward. It's ornament and engineering fused into one gesture. And then there's the oculus itself. You might think cutting a 9-meter hole in the top of a dome would weaken it catastrophically, but the opposite is almost true. The ring of concrete around the oculus acts as a compression ring, gathering the forces from the dome and distributing them evenly around the opening. It's the same principle that makes a manhole cover's circular opening stable. A ring in compression is remarkably strong. Rain does come in through the oculus, of course. The floor is slightly convex with drainage holes to handle it. The Romans thought of everything. Now, the Pantheon is the showpiece, but Roman vaulting and dome construction showed up everywhere. In basilicas, in the great halls of the imperial baths, in market halls like Trajan's Market in Rome, which used a series of groin vaults to create a multi-story covered shopping arcade that feels startlingly modern. The Basilica of Maxentius, completed by Constantine around 312 CE, had a central nave roofed with 3 enormous groin vaults, each spanning about 25 meters. Only a fraction of it survives, but even the surviving fragment, one of the 3 side bays, is massive enough that Michelangelo reportedly studied it while designing St. Peter's Basilica over 1,000 years later. But here's the thing about Roman engineering that's easy to overlook when you're marveling at the Pantheon or the aqueducts. The empire didn't just build spectacular individual structures. It built systems, networks. The road network alone eventually stretched to something like 80,000 kilometers of paved roads connecting every corner of the empire, from Hadrian's Wall in northern England to the deserts of North Africa, from the Atlantic coast of Spain to Mesopotamia. And every one of those roads needed bridges. The Romans built thousands of bridges, many of them using semicircular stone arches, and dozens of them are still standing and still carrying traffic 2,000 years later. The Pons Fabricius in Rome, built in 62 BCE, still carries pedestrians across the Tiber today. Think about that. A bridge built before Julius Caesar crossed the Rubicon, and you can walk across it right now. And this vast network of infrastructure required something else, something we don't always think of as engineering but absolutely is: organization, project management, logistics. The Romans developed sophisticated systems for surveying land, estimating materials, managing labor forces, and maintaining infrastructure after it was built. Frontinus, the water commissioner we talked about, wasn't just documenting the aqueducts for posterity. He was creating an operations manual. He cataloged every pipe diameter, every distribution point, every illegal tap he discovered. He was, in a very real sense, the first infrastructure manager we have a detailed record of. And that tradition of systematic documentation, of treating infrastructure as a living system that needs ongoing care, is something that would be largely lost for centuries after Rome fell. Which brings us to one of the most fascinating and underappreciated chapters in the history of civil engineering: what happened when the Roman Empire collapsed in the West. Because the common narrative, the one most of us absorbed in school, is that the fall of Rome plunged Europe into the Dark Ages, a period of ignorance and stagnation where all the accumulated knowledge of the ancient world was simply forgotten. And that's not exactly wrong, but it's far too simple. The reality is more nuanced, more interesting, and in some ways more instructive about how engineering knowledge actually works. When the Western Roman Empire disintegrated over the course of the 5th century, what collapsed wasn't just a political entity. It was the economic and administrative system that made large-scale engineering possible. You can know how to build an aqueduct, but if there's no centralized authority to commission it, no tax revenue to fund it, no organized labor force to construct it, and no bureaucracy to maintain it, that knowledge becomes academic. And that's largely what happened. The Roman roads continued to be used, but they weren't maintained. Bridges were patched, but rarely replaced when they failed. The aqueducts of Rome itself gradually fell into disrepair as the population of the city shrank from perhaps 1 million people at its peak to maybe 20 or 30,000 by the 6th century. Imagine that. A city built for 1 million people, slowly emptying, its magnificent infrastructure crumbling around the remaining inhabitants, who no longer had the resources or the organization to keep it running. But knowledge didn't simply vanish. It migrated. It transformed. It went underground in some places and flourished in others. The Eastern Roman Empire, what we call the Byzantine Empire, continued for another 1,000 years, and Byzantine engineers carried forward Roman techniques while developing innovations of their own. The Hagia Sophia in Constantinople, completed in 537 CE under Emperor Justinian, is in many ways the successor to the Pantheon. Its main dome spans about 31 meters, smaller than the Pantheon's, but it sits on 4 enormous arches supported by pendentives, triangular curved sections that transition from the square base to the circular dome. This was a revolutionary structural concept. The Pantheon's dome sits on a circular drum, which is geometrically straightforward. But placing a dome on a square plan using pendentives opened up entirely new architectural possibilities. It meant you could have a large domed space with clear walls on 4 sides, filled with windows. When you step inside the Hagia Sophia, the dome seems to float on a ring of light. 40 windows pierce the base of the dome, and the thin ribs between them are almost invisible from below. Procopius, the contemporary historian, wrote that the dome seemed to be suspended from heaven by a golden chain rather than resting on solid masonry. The engineering reality was more fraught than the poetry suggests. The original dome partially collapsed in 558, just 20 years after completion, damaged by earthquakes. It was rebuilt with a slightly higher profile, making it more pointed, which reduced the outward thrust at the base. The architects, Anthemius of Tralles and Isidore of Miletus, a mathematician and a physicist, notably, not just builders, had pushed the structural limits of masonry construction to their edge, and the edge pushed back. But the rebuilt dome has stood for nearly 1,500 years now, through dozens of major earthquakes, which tells you that the adjustment worked. Meanwhile, in the Islamic world, engineering was not just preserved, but actively advanced. When Arab armies swept through the former eastern provinces of the Roman Empire in the 7th century, they inherited a rich tradition of Roman and Byzantine construction, and they merged it with Persian engineering knowledge. The result was a golden age of civil engineering that produced innovations in hydraulics, in structural design, and in urban planning that were centuries ahead of anything happening in Western Europe at the same time. Islamic engineers developed the Qanat system, long underground channels that transported water from mountain aquifers to arid lowlands using nothing but gravity, sometimes running for kilometers through carefully graded tunnels. They refined the pointed arch, which is structurally superior to the Roman semicircular arch, because it directs forces more vertically, reducing the outward thrust on the supports. This is a subtle but crucial point, and it's one that would eventually change everything about how buildings were made in Europe. Because the pointed arch didn't stay in the Islamic world, it traveled through trade, through the Crusades, through Spain, where Islamic and Christian cultures rubbed shoulders for centuries. And when it arrived in medieval Europe, it unlocked something extraordinary. Let's set the scene. It's the 11th, 12th century in Western Europe. The Roman organizational machine has been gone for 600 years. The great concrete recipes are lost, or at least, nobody is mixing pozzolanic concrete on an industrial scale anymore. Most construction is heavy, thick-walled Romanesque, round arches, barrel vaults, massive piers, beautiful in its own stolid way, but limited. If you want to build a tall church with a wide nave, you've got a problem. Those semicircular arches push outward, hard. To resist that thrust, you need enormously thick walls, and thick walls mean small windows. Small windows mean dark interiors. Walk into a Romanesque church, and you'll notice it right away. It feels like a fortress, solid, reassuring, but dim. Now imagine you're a bishop in northern France around 1140, and you want your cathedral to feel like the kingdom of heaven. You want light, you want height, you want your congregation to walk in and look up and feel something transcend the ordinary weight of stone. You need a structural revolution. And here's where the pointed arch changes the game. Remember how the semicircular arch pushes outward because its curve is wide and the forces at the base splay apart? The pointed arch gathers those forces more steeply, channeling them downward through the supports rather than outward against the walls. That single geometric shift means your walls don't have to be as thick. They don't have to do as much work resisting lateral thrust, which means, and this is the leap, you can start cutting holes in them. Big holes. Holes you can fill with glass. But the pointed arch alone wasn't enough. Medieval masons combined it with two other innovations to create what we now call Gothic architecture. And when you see all three working together, it's genuinely one of the most elegant structural systems ever devised. The first is the ribbed vault. Instead of building a solid barrel vault or even a groin vault the way the Romans did, Gothic builders constructed a skeleton of stone ribs, pointed arches crossing the ceiling diagonally and along the ridgelines, and then filled in the spaces between the ribs with thin panels of stone. Think of it like an umbrella. The ribs are the metal struts, and the fabric between them carries almost no structural load. This meant the ceiling could be much lighter, which meant the supports below didn't need to be as massive. The second innovation is the flying buttress, and this one is just brilliant. Here's the thing. Even with pointed arches and ribbed vaults, there's still some outward thrust. Physics doesn't let you eliminate it entirely. So instead of making the walls thick enough to absorb that thrust internally, Gothic builders externalized the support. They built freestanding stone arches that leaped from the outer wall of the cathedral to a heavy pier standing several meters away. These are the flying buttresses, and they act like hands pressing against the building's sides, catching the outward push of the vault and redirecting it down through the pier into the ground. The wall itself is freed from structural duty. It becomes, essentially, a curtain, a frame for glass, and that's how you get those impossible windows. Chartres Cathedral, consecrated in 1260, has something like 2,000 square meters of stained glass. The walls are more glass than stone. From the inside, on a sunny day, the effect is overwhelming. Columns of colored light pouring through vast windows that seem to dissolve the boundary between the building and the sky. It's architecture as theology, and it's made possible by pure structural engineering. The person often credited with launching this revolution is Abbot Suger of Saint-Denis, who in the 1140s rebuilt the choir of his abbey church near Paris, using pointed arches and large windows. Suger wasn't an engineer. He was a churchman and a politician, close advisor to the French king. But he had a vision of sacred space filled with light, and he found masons who could make it real. The rebuilt Saint-Denis is generally considered the first Gothic building, and within a generation, the idea spread across northern France like wildfire. Sens, Noyon, Lyon, Paris, Chartres, Reims, Amiens, cathedral after cathedral rose higher, wider, lighter, and this is where the human drama gets fascinating, because what followed was essentially a building race. Each city wanted its cathedral to be taller than the last. Chartres reached about 37 meters to the vault. Reims pushed to 38. Amiens hit 42. And then Beauvais tried for 48 meters, the tallest Gothic vault ever attempted. The choir was completed in 1272, and it was breathtaking for 12 years. In 1284, part of the vault collapsed. The piers were too slender, the spans too ambitious. The masons had found the limit. Beauvais was partially rebuilt with additional supports, but the full cathedral was never completed. The transept wasn't finished until the 16th century, and the nave was never built at all. To this day, Beauvais Cathedral is an incomplete masterpiece, a monument to both the ambition and the limits of Gothic engineering. What's remarkable is how much the medieval masons achieved without formal engineering theory. They had no calculus, no structural analysis, no way to calculate stresses in a member the way a modern engineer would. What they had was accumulated craft knowledge, passed from master to apprentice, encoded in geometric rules of thumb. They knew that if you made a buttress a certain proportion of the span, it would hold. They knew that certain arch profiles were more stable than others. They tested by building, and when something failed, they learned. Painfully, sometimes fatally. Construction accidents were common. Scaffolding collapses, vault failures during construction before the mortar had fully cured, stones falling from great heights. The medieval building site was a dangerous place. But here's what's really clever about the Gothic system from an engineering perspective. It's honest. The structure is visible. You can look at a Gothic cathedral and actually read how the forces flow. Down through the ribs, out through the flying buttresses, down through the piers into the foundation. There's very little hidden. Compare that to the Pantheon, where the concrete dome conceals its internal structure, or a modern steel frame building where the skeleton is buried behind cladding. A Gothic cathedral wears its engineering on the outside. Every element you see is doing something. Now, while all this was happening in Europe, let's not forget what was going on elsewhere in the world, because civil engineering is a global story and always has been. In China, engineers were solving problems of extraordinary scale. The Grand Canal, connecting Beijing in the north to Hangzhou in the south, was extended and unified during the Sui dynasty around 605 to 611 CE, a waterway stretching roughly 1,700 kilometers, making it the longest artificial river in the world. It required locks, embankments, and careful grading across varied terrain. Millions of laborers worked on it, and the human cost was staggering. Some accounts suggest that hundreds of thousands died during the Sui-era construction campaigns. The canal transformed Chinese commerce and governance, allowing grain from the fertile south to feed the armies and bureaucracies of the north. It's still in use today, parts of it over 1,400 years old. Chinese bridge engineering was equally impressive. The Jiaozhou Bridge, built around 605 CE by the engineer Li Chun, is the world's oldest standing open spandrel stone arch bridge. It spans about 37 meters across the Jiao River in Hebei province. What makes it remarkable is the open spandrels. The spaces above the main arch near the abutments are not filled with solid stone but are themselves small arches. This reduces the bridge's weight by about 15%, which reduces the load on the foundations, and it also allows floodwaters to pass through the openings rather than pushing against a solid wall of masonry. Li Chun figured this out 1,400 years ago. European engineers wouldn't build comparable open spandrel bridges for another 7 or 8 centuries. And in the Americas, civilizations were engineering on a massive scale without iron tools, without the wheel for transport, and without draft animals. The Inca road network, the Chapak Ñan, stretched roughly 30,000 kilometers through some of the most extreme terrain on Earth. Coastal deserts, mountain passes above 4,000 meters, tropical river valleys. The roads included suspension bridges made from woven grass cables, some spanning gorges 60 meters wide, rebuilt every year or two by local communities as a form of labor tax. The engineering wasn't just the roads themselves, but the system, relay runners, storehouses, way stations, that made the network function as infrastructure. The Romans would have recognized the thinking, even if the materials were utterly different. So by the late medieval period, let's say the 14th, 15th century, you've got this rich global tapestry of civil engineering knowledge. Gothic cathedrals in Europe, massive hydraulic works in China and the Islamic world, road and bridge networks in South America, and all of it built on empirical knowledge. Learning by doing, by failing, by watching what worked, and passing that knowledge down through guilds and apprenticeships and oral tradition. What's missing is a theoretical framework. Nobody can calculate the stress in a beam or predict exactly when an arch will buckle. That's about to change, and the person who starts the change is someone you might not immediately associate with engineering at all. He's a painter, a sculptor, an anatomist, and an inventor, and he's working in Florence in the late 15th century, filling notebooks with sketches of machines and structures and observations about how forces move through materials. Leonardo da Vinci. And here's the thing about Leonardo. We tend to think of him as this singular genius floating above the world, but he was deeply practical. He wanted to know how things worked so he could build them. His notebooks are full of canal designs, bridge concepts, fortification plans, studies of water flow. He sketched ideas for temporary military bridges that a small team could assemble in the field. He drew designs for an enormous revolving crane. He studied the way cracks propagate through walls and the way arches distribute weight. And while most of his engineering ideas stayed on paper, many were ahead of what the materials and manufacturing of his time could deliver. What matters is the approach. Leonardo was trying to reason from principles. He wasn't just copying what the last mason did. He was asking why. Why does this shape hold? Why does water behave this way in a channel? What would happen if I changed this angle? He wasn't alone in this shift either. The Renaissance, broadly speaking, was pulling European thinking toward a more systematic, more questioning relationship with the physical world. But Leonardo is a useful marker because his notebooks sit right at that boundary between the old empirical tradition and the new analytical one. He's sketching and testing and measuring, but he doesn't yet have the mathematical tools, calculus, formal mechanics, to turn his observations into reliable predictions. That would take another couple of centuries. But the door is opening, and the person who really kicks it wide open, at least for the science of structures, is Galileo Galilei. Now, you know Galileo for the telescope, for the moons of Jupiter, for his troubles with the church. But in 1638, near the end of his life, under house arrest and going blind, Galileo published a book called Two New Sciences. And one of those two sciences was essentially the strength of materials. He asked a deceptively simple question. Why can't you just scale things up? Why can't you take a small beam that works perfectly well and build a version 10 times bigger and expect it to hold? He realized that when you double the length of a beam, its weight goes up by the cube, by a factor of 8. But its cross-sectional strength only goes up by the square, by a factor of 4. So bigger structures are proportionally weaker than smaller ones. This is called the square-cube law, and it's one of those ideas that sounds almost obvious once someone explains it. But it's profound. It explains why insects can fall from great heights unharmed, but elephants can't. It explains why you can't just scale up a Gothic cathedral indefinitely, which, of course, is exactly what the builders at Beauvais discovered the hard way in 1284, when their impossibly ambitious 48-meter vault partially collapsed. They didn't have the math to know they were doomed. But Galileo, 3.5 centuries later, could have told them why. Galileo also studied what we'd now call the bending of cantilever beams, a beam fixed at one end with a load on the other. He got some of the details wrong, actually. His analysis of where the beam would break and how the internal stresses distributed wasn't quite right. But the fact that he was even attempting to analyze it mathematically was revolutionary. He was saying, structures aren't magical. They obey laws. We can figure out those laws, write them down, and use them to predict what will happen before we build. And from Galileo, the thread picks up speed. Robert Hooke, in England, publishes his law of elasticity in 1676. Hooke's law, which says that the deformation of a material is proportional to the force applied to it, up to a point. Stretch a spring twice as hard, it stretches twice as far. Load a beam twice as much, it deflects twice as much, as long as you haven't pushed the material past its elastic limit, the point where it starts to permanently deform or break. This is such a foundational idea. Every structural calculation you'll ever encounter rests on some version of Hooke's law. When a civil engineer today designs a steel beam for a building, they're working within the framework Hooke established, making sure the loads stay within the range where the material behaves predictably, proportionally, elastically. Then comes Leonhard Euler in the 18th century, the Swiss mathematician who was so absurdly prolific that there's a joke in mathematics that things are named after the first person to discover them after Euler. Euler tackled the problem of buckling. What happens when you push on a slender column from both ends? Think of pressing down on a thin ruler standing on its end. At some critical load, it doesn't just compress, it suddenly bows sideways and collapses. Euler worked out the mathematics of this in 1757, showing that the critical buckling load depends on the column's length, its cross-sectional shape, and the stiffness of its material. And here's what's really elegant about it. The load at which a column buckles goes down with the square of its length. Make a column twice as long, and it buckles under only 1/4 the load. This is why you see bracing in tall structures, why columns in buildings are broken up by floor plates, why a suspension bridge tower is a complex lattice rather than a simple stick. Euler gave engineers the ability to predict one of the most dangerous failure modes in structures, sudden, catastrophic, without much warning. Now, all of this theoretical work is happening alongside enormous practical changes. The 18th century brings the Industrial Revolution, first in Britain, and it transforms civil engineering in ways that are hard to overstate. The single biggest change? Iron. Specifically, cast iron and then wrought iron, becoming available in large quantities and at falling prices thanks to new smelting techniques. Abraham Darby's coke-fired blast furnaces at Colebrook Dale, starting around 1709. For thousands of years, civil engineers had worked with stone, brick, timber, and earth. These are all materials that are strong in compression. You can stack them, push on them, lean on them, but they're weak in tension. You can't pull on a stone beam very hard before it cracks. That's why arches exist, right? The arch converts what would be a bending and tension problem into a pure compression problem. Every major structural form before iron, the arch, the vault, the dome, the buttress, is basically a clever trick to keep masonry in compression. Iron changes the game because it's strong in tension too. You can pull on it. You can make beams that span longer distances without arching. You can make chains and cables. And the first great demonstration of iron in civil engineering is the iron bridge at Colebrook Dale itself, completed in 1779. It's a single arch spanning about 30 meters across the River Severn, and it's made entirely of cast iron. The designer was Thomas Farnolles Pritchard, though he died before it was finished, and Abraham Darby III oversaw the construction. And here's a lovely detail. Because nobody had ever built a large iron bridge before, they used construction techniques borrowed from timber framing. The joints are dovetails and mortise and tenon connections translated into cast iron. They didn't yet know how to think in iron. They were thinking in wood and executing in metal. It's a perfect snapshot of a technology in transition. But it worked, and it proved the concept. Iron could be a primary structural material. Within a few decades, iron bridges, iron-framed buildings, iron columns, and iron beams were spreading across Britain and then the world. Cast iron gave way to wrought iron, which was more reliable in tension and less brittle. And engineers started pushing the spans longer and the structures taller. This is also when civil engineering becomes a recognized profession. Before the 18th century, there really wasn't a distinction between an architect, an engineer, and a master builder. The same person might design a cathedral, lay out a fortification, and plan a canal. But as the projects got bigger and more technical, specialization crept in. In 1716, France established the Corps des Ponts et Chaussées, the Corps of Bridges and Roads, one of the first formal government engineering organizations in the world. And in 1747, the École des Ponts et Chaussées was founded in Paris as the first engineering school. Think about that. For thousands of years, engineering knowledge was passed down through apprenticeship, through guilds, through watching and doing. Now, for the first time, there's a school where you sit in a classroom and learn the theory: Galileo's beam analysis, Hooke's law, Euler's buckling formulas, before you ever set foot on a construction site. This is a massive shift. It means engineering knowledge can be standardized, tested, debated, improved systematically. In Britain, the professionalization followed a slightly different path. John Smeaton, who rebuilt the Eddystone Lighthouse off the coast of Plymouth in 1759 using a novel hydraulic lime cement that could set underwater, was the first person to call himself a civil engineer, deliberately distinguishing his work from military engineering. In 1771, he and a group of colleagues formed the Society of Civil Engineers, later called the Smeatonian Society, and in 1818, the Institution of Civil Engineers was founded in London, with Thomas Telford as its first president. Telford was a remarkable figure, a self-taught stonemason's son from Scotland, who became the greatest infrastructure builder of his age. He designed roads, bridges, canals, harbors, and churches across Britain. His Menai Suspension Bridge, completed in 1826, used wrought iron chains to span 176 meters across the Menai Strait in Wales, connecting the island of Anglesey to the mainland. At the time, it was the longest suspension bridge in the world. And suspension bridges, let's talk about those for a moment, because they represent something fundamentally different from what came before. An arch works in compression. A suspension bridge works in tension. The deck hangs from cables or chains, which carry the load in pure tension up to the towers, which carry it in compression down to the foundations. It's a beautifully efficient structural form for long spans, because cables are incredibly strong for their weight. You can span distances with a suspension bridge that would be impossible with an arch or a beam. But there's a vulnerability, and it's one that would haunt engineers for the next century and a half. Suspension bridges are flexible. They move, they sway in the wind, and if the wind hits them just right, or if the loads on them set up a rhythmic pattern, they can start to oscillate, to swing back and forth with increasing amplitude. The technical term is aeroelastic flutter, though in the early 19th century, nobody had that vocabulary yet. They just knew that sometimes these bridges moved in ways that were terrifying. Telford's Menai Bridge had trouble with wind almost immediately. A storm in 1839 damaged the deck badly enough that it had to be reconstructed. Other early suspension bridges fared worse. The Brighton Chain Pier, a suspension structure over the sea completed in 1823, was destroyed by a storm in 1836. Engineers kept building them, kept making them longer, kept learning, sometimes the hard way. And the most dramatic lesson of all, the one that every engineering student in the world still studies, was still more than a century away. But the seeds of that disaster were being planted right here in the early 19th century, in the gap between what engineers could build and what they fully understood about how wind and flexible structures interact. That gap between capability and comprehension is one of the recurring themes in civil engineering history, and it was about to widen dramatically as the 19th century brought a material that would reshape the entire built world. Because wrought iron, as useful as it was, had a successor waiting in the wings, one that was stronger, more versatile, and could be produced in enormous quantities. and the story of how that material came to dominate everything, bridges, buildings, railroads, ships, starts with a man named Henry Bessemer and a converter that could turn molten pig iron into steel in a matter of minutes. Bessemer's converter was, in its way, one of those inventions that didn't just solve a problem. It redrew the map of what was possible. Before Bessemer, steel existed, of course. People had been making it for centuries, in small batches, through laborious processes that involved heating wrought iron with carbon, folding it, hammering it, repeating. Beautiful steel, sometimes. Damascus steel, crucible steel, blades and tools and springs. But it was expensive. Far too expensive to build a bridge out of, or a building, or a mile of railroad track. Steel was a specialty material. What the world built with in the mid-1800s was cast iron and wrought iron, each with its own frustrating limitations. Cast iron was strong in compression, but brittle. It could shatter under tension or impact. Wrought iron was ductile and tough, but relatively weak and labor-intensive to produce in large quantities. Steel was the dream material, strong in both tension and compression, ductile enough not to shatter, hard enough to hold an edge or bear a load. If only you could make it cheaply, in bulk. Henry Bessemer figured out how. Or more precisely, he figured out one way how. And he did it with an insight that seems almost counterintuitive. His converter, patented in 1856, worked by blowing air through molten pig iron. That's it, essentially. You take this bath of liquid iron that's full of carbon and silicon and other impurities, and you blast cold air up through it from the bottom. The oxygen in the air reacts with the carbon and burns it off. The reaction is so exothermic, so violently hot, that it keeps the metal molten without any external fuel. In about 20 minutes, you go from pig iron to something very close to steel. The process was spectacular to watch, sparks and flame erupting from the top of the converter like a contained volcano. And it was spectacularly productive. What had taken days or weeks in small batches could now happen in minutes, in tons. Now, Bessemer wasn't the only one working on this. A British metallurgist named Robert Mouchet made critical contributions, figuring out that you needed to add a precise amount of carbon back in at the end through a manganese iron alloy called Spiegeleisen to get the steel's properties right. Bessemer's original process sometimes produced brittle, unusable metal, and Mouchet's fix was essential. There's a whole sad story there about Mouchet not receiving proper credit or compensation for years, his daughter eventually petitioning Bessemer directly, and Bessemer finally granting Mouchet an annual pension. The history of engineering is full of these stories. The person who gets the patent and the person who makes it actually work aren't always the same, and the credit doesn't always land where it should. And across the Atlantic, an American named William Kelly had independently developed a similar air-blowing process even earlier, possibly as early as 1851, though he didn't commercialize it as effectively. Meanwhile, in 1864, the Siemens-Martin open hearth process emerged as a competitor, slower than Bessemer's converter, but more controllable, able to use scrap iron as feedstock, and better at producing steel with consistent, predictable properties. By the 1880s and 1890s, both processes were running full tilt, and the price of steel plummeted. In 1867, steel cost about $170 per ton in the United States. By 1884, it was under $30. Think about what that means. A material that had been precious was suddenly abundant, and that abundance changed everything. Railroads were the first major consumer. Steel rails lasted far longer than iron ones, roughly 10 times longer under heavy traffic. But it was bridges and buildings where steel's impact on civil engineering became truly transformative. And the person who probably best embodies that transformation, at least in the bridge world, is James Eads. Eads is one of those figures who shouldn't have been able to do what he did. He had no formal engineering education. He'd made his fortune as a young man by salvaging wrecked steamboats from the bottom of the Mississippi River using diving bells he designed himself. He knew the Mississippi, its currents, its moods, the way its muddy bottom shifted and scoured, better than almost anyone alive. When St. Louis needed a bridge across that river in the late 1860s, Eads proposed something audacious. A triple-arch bridge made of steel, with foundations sunk to bedrock through the river's deep, treacherous alluvial layers. Nobody had built a steel bridge of that scale before. Nobody had sunk foundations that deep in those conditions. The Eads Bridge, completed in 1874, is a masterpiece, and the story of building it is harrowing. The foundations had to go down over 100 feet below the water's surface, through sand and mud and gravel, to reach limestone bedrock. Eads used pneumatic caissons, essentially giant inverted boxes, open at the bottom, pressurized with compressed air to keep the water out while workers dug inside. The men working in those caissons, deep beneath the river, suffered terribly from what was then called caisson disease. The bends, we'd call it now. Decompression sickness. Nitrogen dissolving into the blood under high pressure, then forming bubbles as the workers returned to the surface too quickly. 15 men died during construction. Many more were permanently disabled. The connection between the pressurized environment and the illness was poorly understood at the time, and the working conditions were brutal. It's one of those moments in engineering history where the human cost of progress is painfully visible, and it deserves to be remembered alongside the technical achievement. But the bridge itself, the bridge was a revelation. Those 3 steel arches, each spanning over 500 feet, demonstrated that steel could do things iron simply couldn't. The arches are ribbed tubes, and Eads specified chrome steel, insisting on testing every single batch. He was obsessive about quality control in a way that was ahead of his time, rejecting material that didn't meet his standards even when it caused delays and cost overruns. The bridge still stands. It still carries traffic. 150 years later. And here's where the story accelerates, because once you have cheap, abundant steel, the question stops being, can we build it? And starts being, how tall, how long, how fast? The late 19th century is when civil engineering enters its heroic age, and the 2 structures that best represent that era, that capture both its ambition and its cost, are the Brooklyn Bridge and the Fourth Bridge. The Brooklyn Bridge you probably know, at least by sight. Those Gothic stone towers with the web of cables stretching between them. It was designed by John Augustus Roebling, a German-born engineer who had already built several successful suspension bridges using wire rope cables, a technology he'd pioneered and manufactured himself. Roebling's insight was that many thin wires, bundled and spun together, could create a cable far stronger and more reliable than the chain links used in earlier suspension bridges like Telford's Menai. He proposed spanning the East River between Manhattan and Brooklyn with a bridge whose main span would stretch nearly 1,600 feet, far longer than anything previously attempted. Roebling never saw it built. In 1869, while surveying the site, his foot was crushed by a ferry against a piling. He developed tetanus and died within weeks. The project passed to his son, Washington Roebling, who was 32 years old. And Washington Roebling drove the project forward with extraordinary determination, until the caissons got him too. Working in the pressurized foundations beneath the East River, he suffered a severe case of decompression sickness that left him largely bedridden for the remaining years of construction. He directed the work from his apartment in Brooklyn Heights, watching through a telescope, communicating through his wife, Emily Warren Roebling, who became the de facto chief engineer on site. Emily Roebling learned the mathematics, the materials science, the contract management. She dealt with politicians, suppliers, and workers. When the bridge opened in 1883, she was the first person to cross it. The Brooklyn Bridge is a monument to the Roebling family, all three of them, and to the idea that engineering is never just one person's achievement. The bridge itself introduced techniques that became standard. Those main cables were spun in place. Individual wires carried back and forth across the river by a traveling wheel, then compacted and wrapped into the massive cables you see today. Each cable contains over 5,000 individual steel wires. The deck is stiffened by trusses to resist wind. The Roeblings were keenly aware of the wind problem that had plagued earlier suspension bridges. They also added diagonal stay cables radiating from the towers, creating that distinctive web pattern. Those stays provide additional stiffness, additional resistance to the kind of oscillation that had destroyed lighter, more flexible suspension bridges. The Roeblings overbuilt the Brooklyn Bridge deliberately, and that conservatism is part of why it's still standing and still carrying traffic today. Now, the fourth bridge, completed in 1890 in Scotland, represents the opposite aesthetic, but the same ambition. If the Brooklyn Bridge is graceful and Gothic, the fourth bridge is muscular and unapologetic, a massive cantilever truss bridge spanning the Firth of Forth in 3 enormous leaps, each over 1,700 feet long. It was designed by Benjamin Baker and John Fowler, and it was built in the shadow of disaster. Because just upstream, in a sense, the Tay Bridge had collapsed. The Tay Bridge disaster of 1879 is one of the most infamous failures in engineering history, and it shaped everything that came after. The original Tay Bridge was designed by Thomas Bouch, a prolific railway engineer who had built dozens of bridges across Britain. His Tay Bridge was a long iron lattice structure crossing the Firth of Tay, nearly 2 miles of bridge, and when it opened in 1878, it was celebrated as a triumph. Queen Victoria crossed it and knighted Bouch. But on the night of December 28, 1879, during a violent storm, the central navigation spans, the high girders, 13 spans in all, collapsed into the river while a passenger train was crossing. 75 people died, every single person on that train. The inquiry that followed was devastating. The bridge's design had inadequately accounted for wind loading. Bouch had used a wind pressure figure that was far too low. The cast iron columns had manufacturing defects, blowholes and imperfections that had been filled with a putty-like material and painted over. The lugs connecting the bracing bars to the columns were poorly designed and poorly cast. The workmanship was shoddy, the inspection was inadequate, and the design margins were too thin. The Court of Inquiry concluded that the bridge was badly designed, badly built, and badly maintained. Thomas Bouch, who had been knighted just months before, was professionally destroyed. He died less than a year after the disaster, broken by the disgrace. So when Baker and Fowler set out to build the fourth bridge just a few years later, they were building in the long shadow of the Tay. And they responded with overwhelming strength. The fourth bridge used 54,000 tons of steel. Its tubular members are enormous, 12 feet in diameter in places. Baker famously demonstrated the cantilever principle using two men sitting in chairs, extending their arms, with a third person suspended between them. A photograph that became one of the most iconic images in engineering history. The bridge was designed for wind loads far beyond anything previously considered. It was, in every way, a declaration that this structure would not fail. And it hasn't. It's still carrying rail traffic today, over 130 years later, and it's a UNESCO World Heritage Site. But here's what's interesting about the contrast between the Tay Bridge and the Forth Bridge, and it connects to something deeper about how civil engineering evolves. Failure, as terrible as it is, teaches. The Tay Bridge disaster didn't just kill 75 people. It fundamentally changed how engineers thought about wind loading, about quality control, about the responsibilities of the designer. It made the Forth Bridge possible, in a sense, by making its designers determined to leave no margin of doubt. And that pattern, catastrophe followed by deeper understanding, followed by better practice, repeats throughout civil engineering history. We saw it with the early suspension bridges and their wind problems. We'll see it again, dramatically, in the 20th century. The gap between what we can build and what we fully understand about how it behaves, that gap never fully closes. It just moves to new frontiers, and in the late 1800s, the frontier was moving upward, because steel wasn't just transforming bridges. It was about to transform cities themselves in a way that would have been literally unimaginable a generation earlier. The problem was simple. Land in cities was expensive and getting more expensive. Manhattan, Chicago, London, these dense urban cores were running out of room to spread outward. The only direction left was up. But you can't build a masonry building much taller than about 10 or 12 stories. The walls at the base have to be so enormously thick to support the weight above that they eat up most of your usable floor space. The Monadnock building in Chicago, completed in 1891, is the ultimate expression of this limit. 17 stories of load-bearing brick, with walls 6 feet thick at the base. It's magnificent, but it's also a dead end. You simply cannot go higher with that approach. What you need is a skeleton, a frame. And this is where a quiet revolution was happening in Chicago in the 1880s, driven by a combination of cheap steel, the invention of the safety elevator, and the desperate need to rebuild after the Great Fire of 1871. The person most often credited with the conceptual breakthrough is William LeBaron Jenney, whose home insurance building, completed in 1885, is frequently called the first skyscraper. Now that claim is debated. Architectural historians love to argue about what counts as a true steel frame versus a hybrid, and the home insurance building used both iron and steel columns. But the principle Jenney established was the one that mattered. Instead of the walls holding up the building, the frame holds up the building, and the walls are just a skin, a curtain hung on that frame. The walls don't carry load anymore. They just keep the weather out. And once you grasp that distinction, once the structure becomes a cage of steel rather than a stack of stone, there's no theoretical limit to how high you can go. The practical limits, sure, wind, foundation, the sheer logistics of moving people up and down, but the structural concept itself had broken free from gravity in a way that masonry never could. And that realization rippled outward from Chicago like a shockwave. Within a decade, the skyline of Lower Manhattan was transforming. The technology moved fast because the economics demanded it. Land in downtown New York by the 1890s could cost more per square foot than the building sitting on it, So every additional story you could stack on top of that land was essentially free real estate, pure profit. The math was irresistible, and the engineers and architects who understood steel framing found themselves in a kind of arms race, not just for height, but for efficiency. How light could you make the frame? How quickly could you erect it? How much usable floor space could you squeeze out of every story? The early skyscrapers taught engineers something important about wind. Not the catastrophic wind loading that had brought down the Tay Bridge, though that lesson was very much alive in everyone's mind, but the subtler, everyday problem of a tall building swaying in an ordinary breeze. A 10-story masonry building is so heavy and rigid that wind barely registers. But a 20-story steel frame is lighter, more flexible, and it moves, not a lot, not dangerously, but enough that people inside can feel it, and that feeling is deeply unsettling when you're sitting at a desk on the 18th floor and your coffee starts gently sloshing in its cup. So engineers had to think about stiffness in a new way. Not just, will this building stand up, but will the people inside it feel comfortable? That's a very different design criterion, and it pushed the development of bracing systems, cross-bracing with diagonal members that triangulate the frame and resist lateral forces. You're basically turning the building into a giant truss, using the same geometric principle that had made those railway bridges so effective. But here's the thing about going up. You also have to go down. Every one of those steel columns has to transmit its load into the ground, and the ground in Manhattan is not uniformly cooperative. Parts of lower Manhattan sit on solid bedrock. Manhattan schist, a beautiful, hard, metamorphic rock that's close to the surface near the southern tip, and again in Midtown. But between those two zones, roughly in the area we now call Greenwich Village and Soho, the bedrock dips down, sometimes 60 or 70 feet below the surface, buried under soft clay and sand and fill. And this is actually one of the reasons the classic Manhattan skyline has that distinctive two-humped shape. The cluster of skyscrapers downtown, a gap in the middle, and then another cluster in Midtown. For decades, people assumed this was purely because of the bedrock depth, that it was simply too expensive to sink foundations through all that soft material. More recent research suggests the economics and zoning played a bigger role than geology alone, but the foundation challenge was absolutely real, and it forced some remarkable engineering. The solution, in many cases, was caissons, the same basic technology that Eads had used for his bridge piers in St. Louis, sunk down through the muck to reach solid rock. For the tallest buildings, nothing else would do. You needed that direct connection between the steel skeleton above and the unyielding rock below, a continuous path for the loads to travel. And as buildings got taller through the early 20th century, the foundation work became its own specialized discipline, with its own experts, its own techniques, its own dangers. Now, while all of this vertical ambition was reshaping cities, something equally transformative was happening horizontally. And it was happening because of a material we haven't really talked about yet, even though it's arguably the single most important material in the entire history of civil engineering. I'm talking about reinforced concrete. Plain concrete, as we discussed way back with the Romans, is ancient. The Romans made extraordinary things with it. But plain concrete has a fundamental limitation that we should revisit, because understanding it is the key to understanding why reinforced concrete changed everything. Concrete is phenomenally strong in compression. You can stack enormous weight on top of it, and it just sits there, absorbing the load. But it's weak in tension. If you try to pull it apart or bend it so that one face is being stretched, it cracks, and it cracks suddenly. without much warning. This is why Roman concrete structures are almost exclusively arches, vaults, and domes, shapes that keep the material in compression. The Romans couldn't build a concrete beam to span a gap the way you'd use a wooden beam or an iron girder, because the bottom face of that beam would be in tension and the concrete would simply crack and fail. The insight that transformed concrete was beautifully simple. Embed iron or steel bars inside it, positioned exactly where the tension will occur. The concrete handles the compression, the steel handles the tension, and together they create a composite material that's strong in both. It's a partnership, and it works because of a lucky coincidence of physics. Steel and concrete expand and contract at almost exactly the same rate when temperature changes. If they didn't, the two materials would fight each other as the seasons shifted, cracking and separating. But they don't. They move together as if they were made for each other. The development of reinforced concrete wasn't a single eureka moment. It was a slow accumulation of experiments across several countries during the mid to late 19th century. A French gardener named Joseph Monnier is often credited as a pioneer. He was embedding iron mesh in concrete to make garden pots and planters in the 1860s, and he patented the technique in 1867. But he wasn't really thinking about structural theory. He just noticed that his pots didn't crack as much when they had wire in them. The more systematic engineering understanding came from people like François Hennebique, a French contractor who developed a comprehensive system for reinforced concrete construction in the 1890s. Beams, columns, slabs, all working together as a monolithic frame. Hennebique was a brilliant self-promoter, as well as a gifted engineer, and he built hundreds of structures across Europe, proving that reinforced concrete could do nearly anything steel could do, often more cheaply. And cheaply is the key word. Steel was getting less expensive thanks to Bessemer and the open hearth process, but it still required specialized mills, skilled fabricators, and careful assembly on site. Concrete, on the other hand, could be made from cement, sand, gravel, and water, materials available almost everywhere. You could mix it on site, pour it into wooden forms of almost any shape, drop in your steel bars, and let it harden. You didn't need a steel mill. You didn't need riveting crews working at dangerous heights. You needed laborers, carpenters to build the formwork, and an engineer who understood where to place the reinforcement. This made reinforced concrete enormously attractive for the kinds of infrastructure that the rapidly industrializing world desperately needed: bridges, dams, water treatment plants, sewers, tunnels, factory floors, grain silos, retaining walls, the unglamorous backbone of modern civilization. One person who grasped the potential of reinforced concrete more fully than almost anyone was Robert Maillard, a Swiss engineer working in the early 20th century. Maillard designed bridges, mostly in Switzerland, and what made his work extraordinary was his ability to see reinforced concrete not as a substitute for stone or steel, but as something entirely new, a material that could be shaped into thin, elegant curves that were simultaneously structure and form. His Salzgitter Bridge, completed in 1930, spans a gorge in the Swiss Alps with a three-hinged concrete arch that's breathtakingly slender. It looks almost impossibly thin for its span of about 90 meters, and the reason it works is that Maillard understood exactly how forces flow through a curved concrete form. He didn't just calculate the structure, he sculpted it, removing material wherever it wasn't needed, thickening it wherever stress concentrated. The result is something that looks like art, but is really pure engineering logic made visible. But reinforced concrete also introduced new ways for things to go wrong. The steel inside is hidden. You can't see it. You can't easily inspect it. If water seeps through cracks in the concrete and reaches the steel corrodes, and as it rusts, it expands, which cracks the concrete further, which lets in more water, which causes more corrosion. It's a vicious cycle, and it's the reason so many reinforced concrete structures from the mid-20th century are now crumbling. Bridges, parking garages, highway overpasses, the ones built in the great infrastructure boom of the 1950s and 1960s, are reaching the end of their design lives, and in many cases they weren't detailed carefully enough to keep water away from the reinforcement. The salt spread on winter roads accelerates the corrosion dramatically. This is one of the great slow-motion infrastructure crises of our time, and it's largely invisible to the public until a chunk of concrete falls off an overpass or a bridge gets suddenly closed, which brings us to something that was emerging alongside reinforced concrete and steel frame skyscrapers. The automobile and the staggering infrastructure demands it created. Because here's what happened in the 20th century that reshaped civil engineering more profoundly than any single invention. The car went from curiosity to necessity in barely 2 generations, and the entire built landscape of the developed world was rebuilt to accommodate it. Roads, highways, bridges, tunnels, interchanges, parking structures, gas stations, suburban subdivisions. The sheer volume of civil engineering work triggered by the automobile is almost impossible to overstate. And the person who arguably did more than anyone else to shape that transformation, at least in the United States, was not an engineer at all, but a bureaucrat, an urban planner named Robert Moses. Moses never held elected office, but from the 1920s through the 1960s, he controlled the construction of virtually every major piece of public infrastructure in New York: bridges, highways, parks, housing projects, tunnels. He built the Triborough Bridge, the Verrazano Narrows Bridge, the Cross Bronx Expressway, Jones Beach, Lincoln Center. The scale of his influence is hard to comprehend, and the engineering he commissioned was often superb. The Verrazano Narrows Bridge, completed in 1964, was the longest suspension bridge in the world at the time, with a main span of just over 4,200 feet, and its towers are so tall and so far apart that they actually had to account for the curvature of the earth in the design. The tops of the towers are slightly farther apart than the bases by about 1 5/8 inches because of the planet curving away beneath them. Think about that for a second. A bridge so large that the roundness of the earth becomes a measurable factor in its geometry. But Moses also embodied a darker side of 20th century civil engineering: the willingness to demolish entire neighborhoods, displace tens of thousands of people, and prioritize automobile traffic over communities, over public transit, over the human fabric of cities. The Cross Bronx Expressway alone destroyed the homes of thousands of families and carved a wound through the South Bronx that the neighborhood arguably never recovered from. And Moses wasn't unique. Highway engineers across America were doing the same thing, routing interstate highways through the hearts of cities, almost always through poor and minority neighborhoods that lacked the political power to resist. The engineering was competent. The concrete was sound. The bridges held up. But the human consequences were devastating, and they forced a reckoning that's still ongoing about what civil engineering is actually for, who it serves, whose lives it improves, and whose lives it destroys. And that question, that uncomfortable, necessary question, it didn't go away. It got louder. Because by the 1960s and 1970s, communities started fighting back. In cities across America, People stood in front of bulldozers, organized protests, filed lawsuits, and said no. One of the most famous battles happened in New York itself, where a writer and activist named Jane Jacobs went toe-to-toe with Robert Moses over his plan to run an expressway through Lower Manhattan, right through Washington Square Park, through the heart of Greenwich Village, through one of the most vibrant, walkable, human-scaled neighborhoods in the city. Jacobs wasn't an engineer. She wasn't a planner by training. She was a journalist who had spent years observing how cities actually worked at the street level. The way a mix of old and new buildings created affordable space for small businesses, the way short blocks and diverse uses kept sidewalks alive with people at all hours, the way neighborhoods functioned as complex ecosystems that couldn't be reduced to traffic flow diagrams. Her book, The Death and Life of Great American Cities, published in 1961, was a devastating critique of the kind of top-down, car-centric planning that Moses represented. And she won. The Lower Manhattan Expressway was never built. It was one of the first major highway revolts in America, and it inspired similar fights in San Francisco, in Baltimore, in Portland, in dozens of cities where proposed freeways were stopped, scaled back, or eventually torn down. And here's what matters about that story from an engineering perspective. It wasn't that the engineering was wrong in a technical sense. The highway designs were structurally sound. The traffic models predicted increased throughput. The cost-benefit analyses, narrowly defined, showed positive returns. The failure was in what the models left out. They didn't account for the value of a neighborhood. They didn't measure the cost of displacing a community. They didn't factor in the long-term economic decline that followed when you severed a neighborhood's connections and filled it with exhaust fumes. The engineering was answering the wrong question. It was optimizing for vehicle movement when it should have been optimizing for human flourishing. And that realization, that civil engineering is never just about the structure, that it's always embedded in social and political and economic contexts, that became one of the defining lessons of the 20th century. But let me come back to the structures themselves for a moment, because the 20th century also gave us some of the most dramatic structural failures in history, and each one taught engineers something they didn't know. And the one I've been wanting to tell you about, the one that changed how engineers think about the relationship between structures and the forces of nature, happened on a cold, windy morning in Washington State. The Tacoma Narrows Bridge, November 7th, 1940. You may have seen the footage. It's one of the most famous pieces of engineering film ever recorded. The bridge, a suspension bridge spanning the Tacoma Narrows in Puget Sound, had been open for only about 4 months when it began to oscillate violently in a 42-mile-per-hour wind. Not a hurricane, not an extraordinary storm, just a steady, moderate wind. And the bridge didn't just sway, it twisted. The deck rolled and undulated in a way that looked almost alive, almost like a ribbon being shaken. The oscillations grew larger and larger over the course of about an hour until the deck tore itself apart and collapsed into the water below. Remarkably, only one life was lost. A dog named Tubby, trapped in a car on the bridge that its owner had to abandon. The human toll was minimal, but the engineering lesson was enormous. Now, the common explanation you'll hear is that the wind hit the bridge at its natural resonant frequency, like a singer hitting the right note to shatter a glass. And that's not quite right. What actually happened was something called aeroelastic flutter, a self-exciting oscillation where the wind doesn't just push the structure, it interacts with the structure's own motion in a feedback loop. As the deck twisted one way, its new angle changed how the wind flowed over it, which created forces that twisted it further, which changed the airflow again, and so on. It wasn't that the wind happened to match the bridge's frequency. It was that the bridge's own shape and flexibility created conditions where energy from the wind was continuously fed into the oscillation instead of being damped out. The bridge was essentially extracting energy from a steady wind and converting it into ever larger motion. And the reason this happened to the Tacoma Narrows Bridge and not to other suspension bridges was its design. It used a very shallow, solid plate girder for the deck instead of the deep, open truss structures that earlier suspension bridges like the Golden Gate or the George Washington Bridge had used. That shallow, solid profile was aerodynamically unstable. It was like the difference between holding a flat sheet of paper in the wind versus a piece of window screen. The solid surface catches the wind in ways that create complex, dangerous aerodynamic effects. And here's the thing. The engineer who designed it, Leon Moisseiff, wasn't incompetent. He was actually one of the most respected bridge engineers in America. He'd worked on the Manhattan Bridge. He'd contributed to the design of the Golden Gate. He was pushing the boundaries of suspension bridge design toward longer, lighter, more slender structures, and for a while, that approach seemed to be working beautifully. The Tacoma Narrows Bridge was elegant, economical, and, in calm conditions, perfectly functional. The problem was that the engineering profession's understanding of wind effects on bridges was incomplete. They knew about static wind loads, the steady push of wind against a structure. They had design codes for that. What they didn't fully understand was the dynamic interaction between wind and flexible structures, the way aerodynamic forces could couple with structural motion to create instability. It was a gap in knowledge, and it took a spectacular, highly visible failure to close it. After Tacoma Narrows, everything changed. Bridge engineers began working with aerodynamicists. Wind tunnel testing became standard practice for major bridge designs. New deck profiles were developed, open trusses, slotted decks, aerodynamically shaped box girders, all designed to let wind pass through or around the deck without creating those dangerous feedback loops. Every major suspension bridge built since then, the Severn Bridge in England, the Humber Bridge, the Akashi Kaikyo Bridge in Japan with its record-breaking main span of over 6,500 feet, all of them were shaped by the lessons of that November morning in 1940. The failure of the Tacoma Narrows Bridge didn't just fix one bridge. It created an entirely new field of study, bridge aerodynamics, and it's a perfect example of how civil engineering advances through the painful, humbling process of discovering what you didn't know. And that pattern, build, fail, learn, build better, it runs through the entire history we've been tracing tonight. From those first Sumerian irrigation channels that silted up and had to be redug, to the Romans figuring out which volcanic ash made the best concrete, to the Gothic builders at Beauvais pushing their cathedral too high and watching it fall, to the cast iron bridge at the River Tay that couldn't handle the wind it was never designed for. Every failure is a lesson encoded in the built environment, and every code provision, every safety factor, every design standard you've never heard of exists because somewhere, sometime, something went wrong and engineers said, never again. Which brings us, gently, to where civil engineering stands now, in the 21st century. And the challenges are enormous, maybe the biggest the profession has ever faced, because the world is urbanizing at an extraordinary rate. In 1950, about 30% of the world's population lived in cities. Today, it's over 55%. By 2050, it's projected to be nearly 70%. That means billions more people needing water systems, sewage treatment, roads, bridges, buildings, power grids, flood protection, all the invisible infrastructure that makes urban life possible. And all of it has to be built in a world where the climate is changing, where sea levels are rising, where extreme weather events are becoming more frequent and more severe. Think about what that means for a civil engineer designing a coastal flood barrier today. You can't just look at historical storm data and design for the worst storm of the past century. You have to design for storms that haven't happened yet, in a climate that's shifting in ways that are still being understood. The return period calculations that engineers have relied on for decades, the idea of a 100-year flood or a 500-year storm, those are based on the assumption that the past is a reliable guide to the future. And that assumption is breaking down. A 100-year flood isn't a flood that happens once every 100 years. It's a flood that has a 1% chance of happening in any given year, based on historical data. But if the underlying climate is changing, the historical data doesn't capture the future risk. Engineers are having to rethink the very foundations of how they assess and design for natural hazards. And then there's the infrastructure we already have, the bridges and tunnels and water mains and sewer systems built decades ago, many of them approaching or exceeding their design lifetimes. In the United States alone, the American Society of Civil Engineers regularly grades the nation's infrastructure, and the grades are not good. Tens of thousands of bridges are classified as structurally deficient. Water mains break hundreds of thousands of times a year, losing trillions of gallons of treated water. The problem isn't that we don't know how to build good infrastructure. We do, better than ever. The problem is maintenance, funding, political will. It's not glamorous to repair a sewer line. Nobody cuts a ribbon at a pipe relining ceremony. But that hidden, unglamorous work is what keeps cities functioning, and the slow neglect of it is one of the quiet crises of our time. And yet, and this is important, there's also extraordinary innovation happening. Engineers are developing self-healing concrete that uses bacteria embedded in the mix to fill cracks as they form, extending the life of structures by decades. They're using fiber-reinforced polymers that don't corrode the way steel does, solving that hidden reinforcement problem we talked about earlier. They're building with mass timber, engineered wood products like cross-laminated timber that can be used for buildings 10, 15, even 20 stories tall, sequestering carbon instead of emitting it. They're using computational design tools that can optimize structures in ways that would have been unimaginable to Euler or Navier, finding forms that use the minimum material for the maximum strength, creating structures that look almost organic because they've been shaped by the same logic that shapes bones and trees, material only where the forces demand it. And there's a deeper shift happening too, one that goes back to that question about who civil engineering serves. The profession is increasingly recognizing that infrastructure isn't just technical, it's social, that the design of a street determines whether a neighborhood is walkable or car-dependent, that the routing of a transit line determines who has access to jobs and who doesn't, that the placement of a levee determines whose homes are protected and whose are sacrificed. Civil engineers are learning, slowly, imperfectly, but genuinely, to listen to communities, to involve the people who will live with the infrastructure in the process of designing it, to think about equity and justice alongside load factors and material strengths. So here you are, lying in the dark, and we've traveled a long way together tonight. From the muddy banks of the Euphrates, where someone first figured out that if you dug a ditch in the right place, water would flow where you needed it, through the geometric precision of the pyramids and the grid cities of the Indus Valley, through Greek tunnels carved from both ends to meet in the middle, and Roman roads that ran straight across continents, and concrete domes that have stood for 2,000 years. Through Gothic cathedrals reaching for heaven and sometimes falling short. Through the Iron Age and the Steel Age and the Concrete Age. Through bridges that stood and bridges that fell and the lessons learned from both. Through the professionalization of a discipline, the rise of cities, the reshaping of landscapes, and the slow, ongoing reckoning with the human consequences of all that building. And the thing that strikes me, looking at all of it together, is how fundamentally optimistic civil engineering is as a human endeavor. Every bridge is an act of faith, faith in the materials, faith in the mathematics, faith that the thing you build today will still be standing tomorrow and the day after and decades from now. Every water system is a promise that when someone turns on a tap, clean water will come out. Every road is a belief that people should be able to get where they need to go. Civil engineers build the world that everyone else lives in, mostly without noticing, and the best of that work is invisible. You only see it when it fails, and the whole point is that it doesn't. So let that settle over you, like the quiet weight of a well-built structure. All those forces in balance, all those loads finding their paths to the ground, all those hidden systems working in the dark, the water flowing, the sewage draining, the foundations gripping the earth, the whole built world holding steady while you rest. And somewhere out there tonight, someone is designing the next bridge, the next tunnel, the next system that will quietly, invisibly make someone's life a little better. That's what civil engineering has always been, from the very first ditch dug in Mesopotamian clay. People solving problems for other people, using the materials the earth provides and the mathematics the universe allows. And that work goes on, steady and patient, like the flow of water finding its level, like the settling of stone against stone, like the long, slow breath you're taking right now as you drift toward sleep.